We're back.
We are back!
Yes.
What's ether?
People have considered a possibility that maybe space is filled with some sort of ether. Wouldn't that be cool? That was in the early 1900s when people thought maybe light travels through some ether, and maybe light traveling in one direction travels at a different velocity than light traveling in a different direction. This was a famous experiments by Michelson and Morley in the beginning of the 20th century. And today we're still sort of asking that question: could there be an ether out there, not like Michelson and Morley's, but an ether for gravity?
Mm-hmm.
Could gravity be traveling in some sort of
So the ether would be the
Ether.
fabric of space.
maybe it would be something separate from the fabric of space, that's sort of embedded in space, that is sort of part of space, but it's separate from space and time itself. And if that were true, then one of the biggest effects you would observe is that gravity would not travel at the speed of light. Gravity would slow down as it travels through this ether.
Mm-hmm.
So in fact, I have worked on this theory. It's called Einstein ether theory. Very, very, very smart people have worked on this theory for the past 20, 30 years. And what do? We take this theory seriously and we say, well, what if this idea is right? Well, if it is right, then it should have observational consequences. And one of them is that gravity will not propagate at the speed of light. And we can calculate by how much. And then we can ask, can we measure the speed of gravity? And guess what? We did!
Yeah.
We just measured it because two neutron stars collided and they produced gravitational waves. And shortly after they collided, they emitted all sorts of powerful X-rays and light that telescopes independently measured. So you can then compare the time of arrival of the light to the time of arrival of the gravitational wave. And through that comparison, we've established to 1 part in 10 to the 15. That is 1 over 1 and then 15 zeros, okay? Or 0.15 zeros and a 1, or 14 zeros and a 1. That is how close to the speed of light we've determined gravity travels. So if gravity were traveling through some sort of ether, then the effect of the ether has to be incredibly dilute, right? Gravity has to lose very, very tiny amounts of energy to the ether as it travels. Otherwise, this observation we've made would be in conflict with the prediction. So that's the game we play, right? We ask, could there be an ether? Could stars that rotate in a right-handed way behave differently from stars that rotate in a left-handed way? Could there be parity violation in nature? Could there be some other field, we call them fields, just like the electricity and the magnetic field that allow radio waves to travel? Radio waves travel in space, right? So they clearly don't need air to travel. When we think that radio waves that you're listening to right now travel in air, right, because we are on Earth. But indeed, that's obviously not the case because we have satellite communication. So they travel without any air at all. So they're really vibrations of these fields. And there's only a very limited number of fields that we know of out there. Gravity is a field. Electricity and magnetism, they form a field. The Higgs boson, this
I've heard of
God
that.
particle, this is a vibration of a field that was observed. Could there be another field, a hidden field that we have not detected yet that interacts with gravity? You can ask that question, and then you can take it seriously, and you can make predictions of, if this is true, then what would we observe? And then we can go and look for it. And so far, we have not seen any deviation. But that's where the game is. There's puzzles in physics. There's puzzles in the universe. There are things we don't understand. We touched on 2 of them. Another one, why is there more matter than antimatter? Have you thought about that? If matter, you know what antimatter is?
I'm not sure.
Antimatter is matter, but with the opposite sign. Opposite charge. Sign is the opposite sign in the charge. But so electrons, they have a negative charge. Okay.
Right.
If I flip the sign of an electron, I create an anti-electron, and an anti-electron is a positron. Okay. These things have been measured. They have been created in the lab on Earth. Many, like over 50 years ago. We've observed them. We've manipulated them. We've created anti-hydrogen. Okay. It potentially has applications for energy production and so on and so forth. But the universe we observe, everything we understand, we touch, we interact with, it's typically matter, right? It's not like we see antimatter stars out there or antimatter planets, right? Everything is matter. So why is there so much matter and almost no antimatter?
I don't know.
I don't know. I don't know either.
What's the difference between antimatter and dark matter?
Antimatter is just regular matter, like electrons and protons and so on, but with the opposite sign. Dark matter is a bizarre idea that is necessary in order to explain the motion of stars in faraway galaxies. It has nothing to do with antimatter. I'll tell you about dark matter in a second. That's another one of those big puzzles we have. But what we understand is that very early in the universe, roughly, if everything is consistent with experiment, roughly the same amount of matter and antimatter should have been created. But if that's true, then today we would see an equal amount of matter and antimatter, an equal amount of protons and antiprotons, of electrons and positrons, and we don't. So something had to break this symmetry very early in the universe, and we don't know what it is. So that's the puzzle. What created so much matter? It's called the baryogenesis puzzle. The genesis of baryons. Baryons, that type of matter. Dark matter is a completely different idea. So people have observed galaxies, and galaxies are these groupings of stars, and the stars move around the center of the galaxy, just like the sun moves around the center of the Milky Way, and all of the planets come along for the ride, right? So we can observe the motion of stars in other galaxies. We can calculate their velocity. Okay, and Newton, even Einstein, of course, but also Newton's theory tells us that things that are they're moving around the center of the galaxy, very close to the center, will move faster than things that are far away from the center. Okay, so the velocity should decrease at a certain rate as you observe stars that are farther and farther out from the center. And there's a very precise prediction of how this velocity should change with separation. And we don't observe that.
Oh.
Oops.
Oops.
We look at all the matter we see there in galaxies, and it's almost like there's this missing matter. And if you imagine that there is this matter that is there but we can't see, then you can match the rotational velocities of these stars. And so then you can consider, well, what kind of matter would that be? Well, it has to be matter that doesn't interact with light. It has to be matter that doesn't produce light. It has to be a very strange type of matter. And we don't know what it is at all. People are looking for this dark matter.
But that's crazy. It has such an effect on galaxies, but yet we can't touch it and measure it?
It's very difficult to measure. Incredibly difficult. So people are looking for it. It's called the search for dark matter, and it's been going on over the past 30 years. People are trying to determine what these particles are. Could it be a particle called an axion that we've never detected? Could it be a particle called a weakly interactive massive particle, a WIMP? We don't know. And once we learn what these particles are, that will be another piece of the puzzle that we're trying to put together. There are all these questions that we have, all these observations that make no sense, and we're trying to put them together. We give this image as physicists. I feel like sometimes like we understand everything. Everything is solved. Just ask a physicist, right? Ask Jeeves. I'll give you the answer. That's not true at all. There's lots of things we understand, and we understand them really well. Okay. Everyone agrees that if I drop an apple, it falls. Right? Everyone agrees that clocks tick at a slower rate on Earth than they do on satellites. We build technology based on these ideas, but there are still things that we don't fully understand. Physics is not over, it's just beginning. And that is the quest we're on, trying to understand these missing puzzles. Taking all of these crazy ideas, even yours, and trying to come up with predictions for what, if your idea is right, what would the universe look like? What would we observe? Can we build a machine to observe it? Isn't it fun?
What would my universe look like if it wasn't expanding?
I have no idea. Give me like 5 to 10 years and I'll try to figure it out.
Well, first of all, it'd be a lot smaller.
Perhaps, yes.
And would that explain not finding dark matter or dark energy?
I don't think we would be able to explain dark matter because this has to do with the motion of stars around galaxies. So even if those galaxies were closer to us, the speeds wouldn't be affected. They would just be affected by the local environment of
In
the
general
galaxy.
relativity of the
Right.
inner stars.
I mean, what matters for how fast the sun moves around the center of the Milky Way has everything to do with the Milky Way and not with how close or far we are from other galaxies or the
but
size
how do
of the
they know
universe.
the stars spinning around these galaxies go faster or faster than they should? Is that
This is measured, so
So-
what we can actually see the light from some of these stars, so we can calculate how rapidly they're moving. Roughly speaking, that's how you do it. In practice, you actually use much more sophisticated statistical methods to measure this. Of course, this motion, these are called galaxy rotation curves because the rotational velocity of stars in galaxies. This is not the only sign we have that dark matter must be present. It turns out that to explain the cosmic microwave background, you also need a good chunk of dark matter in the early universe. Otherwise, these very precise correlations that we observed would not be there. So who knows?
I know.
Who
This is
knows?
fun.
It's a lot of fun.
So
We need more people
Uh-huh.
to think this is fun and help us. We need help.
would you come back and help me again?
I would be delighted. Thank you
Okay.
so much for
Hey,
having me.
so I got our file servers running, and we're going to put you back to your regular scheduled programming right now.
Fantastic.
Okay. Thank you, Nico Yunes.